Episode 3, Cosmetics and Consumer Products. When I say consumer products, I'm thinking of stuff I look for when I shop at a store like Target, including shampoo, body wash, deodorant, diapers, bandages, shaving cream, contact lens solution, petroleum jelly, mouthwash, and others. Some examples of companies in this space include Unilever, who makes products under well-known brand names like Dove, Axe, and Vaseline, Procter & Gamble, owners of Bounty, Gillette, and Head & Shoulders, and Johnson & Johnson, who make Band-Aid, Listerine, and Neutrogena. As I hope to show you in this video with a few examples, the process of manufacturing these products is loaded with problems and considerations for chemical engineers. Let's start by revisiting the Tide Pod example. You know that I think Tide Pods are an absolute marvel. Look at the Tide Pod from the perspective of an engineer and think about what you'd need to know in order to make a Tide Pod. To start, you need to decide how much detergent one pod should contain. This is a big responsibility. Remember the old-fashioned way of doing laundry, the consumer would decide how much detergent they'd need for a given load of laundry. However, with the Tide Pod, the consumer sacrifices this control for convenience. Therefore, you, as the engineer, need to make sure there's enough detergent in a Tide Pod for a range of laundry load sizes. This decision influences everything else about the process, because in order to make more product, you need more raw materials. Related to this idea is that of quality assurance, or determining what is the acceptable tolerance for deviation in detergent amount. Speaking of the raw materials, what are they? Do detergent molecules occur naturally? If so, we need a way to separate them from their natural source. If not, they need to be produced by some type of chemical reaction, followed by a separation process. Remember that separation processes and chemical reaction kinetics are titles of 2 future classes you'll take as a chemical engineer. Next, what about the flow properties of the detergents? They need to be pumped through pipes around the chemical plant. In order to determine what size pumps and pipes you should use, you might need to know the viscosity, surface tension, and density, among other things that you'll learn about in your fluids and transport classes. Remember from class that the wrapping that looks like plastic is actually polyvinyl alcohol, which is water soluble. This is another chemical that must be produced elsewhere in the process, and the engineer must determine the thickness of the film, which will affect how fast it dissolves. You want the film to dissolve at the right time in the washing machine, not when the Tide Pods are sitting on the humid shelf in your laundry room. Finally, the engineer must figure out how to assemble and seal the Tide Pod. This certainly doesn't seem easy, and I'm curious about how exactly this happens too. For another example, what about toothpaste? Looking at the ingredients is an enlightening exercise that can clue you into what the engineer must consider. On my label, it shows abrasives. It makes sense that any product that cleans should be abrasive in order to be effective, but teeth can be sensitive. What type of material is the abrasive made out of, and how large are the particles? How can the engineer control the size of these particles? Next is fluoride. We know that it's good for teeth, but why? And where does it come from? Also included are preservatives that extend the shelf life. How long is the shelf life anyway? Have you ever found a half-used bottle of toothpaste at the bottom of your drawer and wondered if you could still use it? And finally, there are various flavors of toothpaste, including spearmint, peppermint, and menthol. How are these flavorings made artificially? Also, coloring agents, which gives the Crest brand of toothpaste its signature blue and green stripes. Here's an interesting question. Is toothpaste a solid or a liquid? Pause the video now and consider this for a moment yourself. This is an important question that determines how engineers transport toothpaste in large quantities. On the one hand, it deforms to fill the shape of its container, but on the other hand, if you uncap a tube of toothpaste and turn it upside down without squeezing, no toothpaste falls out. In your future fluids class, again, you'll learn how fluids flow. When you think of a fluid, you're probably thinking about Newtonian fluids, like water, that deform at a rate proportional to the shear stress. This is a reason that when you're kayaking, you move through the water faster if you row harder. However, fluids can be non-Newtonian as well, and toothpaste is a great example of this. You can further classify it as a Bingham plastic. The flow characteristics are similar to that of a liquid, but only if the shear stress exceeds a certain value. This is why you need to squeeze the toothpaste to get it out of the tube. For a mesmerizing look at how toothpaste is made, I suggest searching for the How It's Made video clip for toothpaste, which is freely available on YouTube. I could go on for hours about all the things I think about when I go shopping at Target, But in the interest of keeping these videos short, I'll stop here and instead challenge you to notice and think about these things yourself. See you in the next episode.